Okay, Earth, science, science, we don't say that. Just science time. Science time, today we're talking about gravity. Gravity and the universe. For your benefit, this is to save, remember these YouTube videos are posted publicly so that anyone who has the link can, not just if they have the link, anyone who's even searching YouTube can view them, and I do that so that people can use their own personal, well, for one reason is that people can use their own personal YouTubes and watch, they don't have to have their school email watch it. Anyway, but the YouTube videos are posted publicly, and this, because my normal lavalier mic that I use is dead, I'm using this Blue Yeti mic, but it will hear everything you do. That little clicking noise you just made, you insect, that will be picked up by the mic. This will hear. I have it set to what's called a shotgun mic, so it's lined up to only mostly pick up sound in this direction, but it will hear everything you say. So be very careful with your words. You should be careful with your words anyway. We've just had a discussion about the metaphorical filter between it heard that, Garrett had heard that. The commenter was able for this video, but someone is going to put in the comments if they could. I heard you, Garrett, because they did. What was I saying? Oh, we just had a discussion about the metaphorical filter that exists in your metaphorical head. Good filter today, because I don't want to have to do this YouTube because it's going to be. We have to talk about gravity. Let's talk about gravity. Gravity is the force, one of the four fundamental forces. Define the word fundamental for me. Cool.
Basic.
Okay, yeah, that's a good synonym. So let's expand that a little bit. Very good job, though.
Building blocks.
Mm-hmm. Yep. The basic forces of the universe, the building block force of the universe, the forces of the universe into which we can reduce all the other forces. For instance, you know about a lot of kinds of forces generally from the beginning of the year, or maybe from your just like the spring force, the force the spring exerts. Friction is a force. The force of Peyton pushing Kylie down the stairs. All those kinds of forces are actually could be broken up into the four fundamental forces. And I think in every one of those examples, they are actually reflections of the electromagnetic force, except for the one of the falling down of the stairs would be gravity. So we're going to list the four fundamental forces, not for the first time this year, but they are still important. So we're going to list them in order from strongest to weakest. Strongest to weakest, and if we were to go up the list the other direction, they are also the longest range would be at the bottom, longest range, and the shortest range is going to be at the top. So we're ordering them 1, 2, 3, 4 from strongest to weakest as we go down, and from shortest to longest as we go down. Does that seem to make sense? The shorter forces would also be stronger ones, and the longer forces would also be weaker ones. Does that make sense to you? Think about it as like when you stretch a rubber band, the force on it gets stronger, but the rubber band itself gets weaker. I don't know, that's kind of a dumpy analogy, but you can, whatever works for you. Just remember, the strongest force in this list is also the shortest range. And they are, and we've talked about this before, but they are the strong nuclear force, strong nuclear, electromagnetism. You remember electromagnetism from earlier in the year, having to do with, guess. I'm underlining the part. Magnets, yeah, and electricity. Yeah, those two things are actually one force, but we talked about both of them kind of separately. And then the weak nuclear force. We haven't really talked about these two. We will talk about them next year when you're in physical science, so hold your shorts. But basically, the strong nuclear force is the force glue that holds the nuclei of atoms together, and the weak nuclear force is kind of a spooky thing that governs the decay of nuclear particles, which would eventually cause nuclear radiation. And then the fourth one, the weakest one, but also the longest range one.
Gravity.
Gravity. Why is this important? Why is it important that it is the weakest? I'm not saying for what physical or metaphysical or even religious reason is gravity the weakest force. I'm not saying why is it that way, but why is it important that we understand that it is the weakest one compared to these other ones? It is several, we say, orders of magnitude. It's hundreds or thousands or even hundreds of thousands of times weaker than these other ones. Why would that be important? Well, let's think about it this way. What holds the atoms together? I just told you. The strong nuclear force. And so if gravity were stronger than the strong nuclear force, the atoms would not be held together. And I'm not saying that it was necessarily, because that's not what this class is about, I'm not saying it was necessarily designed that way, but our universe wouldn't be the same if it weren't that way. What holds you together as an object? You think of yourself as an object. You're really a manifestation of your own environment. But you think of yourself as an object. What holds you together? What's holding this cell here in my right chest to this cell next to it in my right chest? What's doing that? You know? Which of these things?
Gravity.
No, it isn't. That's crazy.
Nuclear.
No, it isn't. It's the electromagnetic force. That's what holds atoms together themselves. So we kind of have this idea of this is an atom. What holds the atom together, because the atom's made of stuff, it's made of quarks, but what holds it together is the strong nuclear force. But what holds it to other atoms is the electromagnetic force, generally, and this is a pretty loose definition. And then when we get a big enough pile of this, it has to be a very, very, very large pile of this, but then when we get a big enough pile of this, planet-sized or star-sized, then gravity is the strongest one. Or, I'm sorry, it's never the strongest one, but it's the one that takes over as a force, because not only is it the weakest, it is also the longest range. So on the universal scale, the reason gravity governs the way things are shaped and the way they function is because it has the longest range, and the universe is very large, and so the long range applies. On the microscopic or submicroscopic or atomic or even quantum level, gravity means almost nothing because it's very, 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 very weak, especially on the scale of these masses. But strong force is certainly much stronger, but doesn't act with a larger range. So there's kind of a give and take with all four of these forces. So which of the four fundamental forces is responsible for the large-scale structure of the universe? You could say they all are, and they do work together. That doesn't mean they have a consciousness, but they all do function within the same realm of forces. But gravity is the main one that structures the universe. On what quantities does gravity depend? We talked about this yesterday. What would make gravity between things stronger? I had yesterday, I think I had a piece of paper. I had a radium rock.
More mass.
Mm-hmm. Greater mass of what? What would make the gravitational force between this and if I drop it, where's it going to go?
Down.
Not just down, not the direction. Where is it going to? Where is it trying to get?
To the core of the Earth.
Yeah, to the center of the Earth. Why the center? Well, it's not. That's kind of like a physical shorthand, like we use that in physics. But here's your boy. Wait, hold on. That's not what I actually look like. I'm not a stick figure. There. Here's your boy. I gotta put the glasses on him, and probably close it. His public. And here's the paper. And it's kind of like physics shorthand that we pretend like everything is attracted to the center of an object. Why? Because it just makes it easier. We know that this whole chunk, what is this? Name the chunk real quick here. What am I representing here? Earth. We know that this whole chunk, every little part of it has mass, and every part of every part attracts every other part due to the gravitational force. But we pretend like, because it's easy, and because it's more or less accurate, that all of the mass is concentrated at this central point. And that's true. We observe that to be true, that when we drop something, it goes toward the center of planet Earth, what we call the center of gravity. COG, center of gravity. Why does it do that? Well, because they both have mass. How can I make this force stronger? How could I make this a stronger force? Like what if I were changing things about the universe? If I were omnipotent and I could change anything about the universe, how can I make that force stronger?
More mass.
More mass of what?
The Earth.
The Earth. More mass of the Earth would certainly do it. What else? More mass of the paper would make the force stronger. What do we call the force of gravity acting on an object? You remember this from the beginning of the year? The force of gravity acting on an object is called what?
Gravitational pull.
Sure. There's another name for it. It's in your explorations too, in case you can't remember from the beginning of the year. Who, based on what I just said, has a stronger force of gravity acting on them?
Cody.
Hold up, I haven't given you the options yet. Is it me or this little piece of paper?
You.
Why? Because Earth is bigger? No, Earth is the same size for both of us, so it must be because I am bigger than the little piece of paper. So what do I call this force of gravity, which is bigger for me than it is for the paper, acting on an object? What's bigger about me?
Math. No.
Mass, yeah, but that's what we're talking about. That's what we just changed. What we call the force of gravity acting on me that is stronger than the force of gravity acting on this little guy.
Wait.
Weight.
I knew that.
I assume you were giving me the word and you weren't telling me to wait because I didn't wait. This video is over. No, I'm just kidding. I'm just kidding. The force of gravity acting on an object is called its weight. We abbreviate that either W, or in this case we usually use F sub G, the force of gravity. You've seen this notation probably in math before, where you use a subscript to indicate what kind of thing you're talking about. Like you might have in a math problem, you might have an x value assigned to a watermelon and an x value assigned to a mango. X sub watermelon and x sub mango. Anyway, we're talking about here the force of gravity, F sub G, is equal to, well, we know the force of gravity gets stronger if the masses get bigger, right? So, and what masses are we talking about? When I say plural masses, what masses are we talking about in this example?
The paper.
The thing we're thinking about, which we'll call M1.
M1, M2, and M3.
What's M2?
The U. The Earth.
The other thing we're talking about. So the force of attraction, the weight between these two objects, M1 and M2, is equal to the product of them divided by, how would we make this force, how else could we make this force stronger?
D2.
What's the D stand for? And it's not D2, it's the distance. We could also reduce the distance between them. Remember I said yesterday that in an orbit, a thing that is orbiting is not far enough away from Earth that it's outside the gravity, but it is, if it eventually gets far enough away that the gravity is no longer strongly acting on it, it's because the distance has increased. So the distance squared, not D2, the distance squared. It depends on the distance between them squared. The distance between what? Well, in this case, it is what we consider to be the center of gravity of the Earth and the center of gravity of the little paper. So there's quite a large distance between them, actually. Something like, I forget exactly, but something like 3,000 meters, I think. There's quite a long ways between the center of Earth and that little paper. And that factors into this equation. And then all of this will not even give us the correct number. There's also a capital G, which we call the universal gravitational constant. So M1 here is mass of object 1. M2 is the mass of object 2. D is the distance between them. I'm going to put distance between the center of gravities, the centers of gravity. And then capital G is the universal gravitational constant.
Distance between
the center of gravities, yeah. What units do we use to measure mass? Remember? What unit do we use to measure mass?
weight, pounds.
No.
The scale.
That's not a unit.
Oh,
In science, what unit do we use to measure mass?
kilograms.
Kilograms. So the masses are both measured in kilograms. What unit do we use in science to measure distance?
Meters.
Meters. And the universal gravitational constant is, if I remember correctly, it is Newton meters squared per kilogram squared. Remember, Newton is a unit of force, and when we multiply all these things together, these eliminate, and we're left with just the force. F sub G is weight, and we measure that in newtons in the SI. What, without doing all the math, what would have the stronger F sub G, the larger force of gravity acting between it? I'll use this example again. This little piece of paper or me? Why? What is different about this equation? Is M1 different?
No.
We can say if M1 is the Earth, then no, that's not different. The Earth has the same mass in both cases. Is M2 different?
Yes.
Is the distance between us, between our center of gravities and the planet Earth, different?
No.
Not, yeah. Maybe my center of gravity is somewhere down here, so if I put this one about the same height, then no. They're not the same. They're not different in distance. But even if it's up here, it's negligible. And is the universal gravitational constant different between them? No, of course not. The definition of the universal gravitational constant is true everywhere in the universe. And speaking of everywhere in the universe, What else is this attracted to?
You.
Mm-hmm. What else?
The wall.
What else? Luke is,
The
what's your
table.
name?
Me.
Yeah.
Garrett.
Garrett. Is Garrett just saying things that he sees?
Yeah.
Yeah. Is that a valid response to this?
Yes.
Yeah, because the real answer is, what else is this attracted to? Every other thing in the universe that has mass. So the joke I love to use, especially with 8th graders, is that your little crush, you know you got a little crush, the little crush that you have is attracted to you. Gravitational.
There you go.
And I'll say the meatier you are, the bigger you are, the more your mass is, the more technically attracted he or she is to you. Because of how it gravitates. Everything in the universe is attracted to every other thing. So your attraction, especially if you're a big guy, is stronger than everything around you. And why then, I think this is the last thing, why then are you, even if you are a big guy, like some people are, even if you are a big guy, why is this piece of paper not just like, zoop, and orbit you?
Big enough.
Yeah, you're not big enough. This thing is actually only, this only ends up being a number even in the 10,000ths or more when we're talking about a very large mass. So we have to consider one of these masses to be very large. So if you're on planet Earth. And by the way, why would your weight, using this equation, why would your weight be less on the moon? Do you have less mass than you do here on the moon? No. The moon has less mass than Earth does. There is less force of gravity because the moon has less mass. You've heard the thing about space that like, oh, you would weigh this much on Jupiter, or you weigh this much on the sun. Well, that's all because those objects have a larger mass. It's not because, and that gets us to the main misconception about all this, is that mass and weight are not the same thing. Here on Earth, we can use them pretty much interchangeably because everything we're used to experiencing is on Earth. So if I say that that Payne's backpack has a mass of 10 kilograms, I would actually be determining the weight of that. I'm measuring the force of gravity on it. But you can use them interchangeably on Earth's surface, which is why there's a confusion. But in reality, weight and mass are different things. And depending on where you go, there are different forces of gravity on you, and therefore you have different weights. Questions?
No.
I'm moving over here because I want to be done. Questions?
No.